Okay, on this video, what I want to talk about is ferrite. And if you haven't seen my natural magnetism video, how natural magnets work, you need to check that out for how my theory says natural magnets work. But as you see, I've got a meter, and I'm going to turn on the continuity, which is, let you know when something's metal giving conduction. That's a copper wire. This is a metal bolt. This is a tip to a screw gun, a Phillips screwdriver. And I'll show you a couple other things. This is just a rare earth magnet out of a car speaker. It's got the steel plate still glued to the rare earth part, if you can see. And I've got a plug on. I use it as an inductor on my Lord Kelvins, and you'll see that. You may have seen that or not. And this is just the apparatus to hook it to my Lord Kelvins system. But the steel plate is glued to the rare earth magnet. Here I have another rare earth magnet, similar to that one, almost the same, with no metal on it. And here I have another rare earth magnet, very weak one. It's the ones you buy for kids in kindergarten or young in elementary school. And then here I have my little string of neodymiums, a big one and 5 little ones. Okay, the point of this is we know that steel has continuity. Copper has continuity, and aluminum, all kinds of conductive metals have continuity. But what I'm going to show here is rare earth magnets do not show continuity. None of them. They do not conduct electricity. Even the neodymiums. Up on the nickel plating it will. But on the ends of these, where the nickel plating's been wore off from me using them so much, which is just the neodymium material, it doesn't show continuity. So my point is, when you pass a magnet past copper coils, you get an electric current, right? Because the copper will conduct electricity, but the magnet won't. And if you saw my video on magnetism, and especially with the video on how vortexes of magnets work, which everything of mass has a vortex from gravity on it, but magnets really intensify that. From the input south to the destination north, one way through it, and you get a diversion off the north around to the south, and that gives you your magnetic field. My point is that if you take an electric current in a wire, and I hook it to this neodymium magnet or a string of them, and then I ground that, to Mother Earth. And let's say the magnets have been made as far as the rare earth materials have been compressed in a press and made into balls or whatever shape, but they're not magnetized yet. To magnetize these, the way they do it is they shoot an electric current in one end of the magnet and it grounds out the other end. And what I'm trying to explain here is when you shut the current off, the copper wires conducting electric current, they do not remain magnetized. They just let the electricity go through it and then stop, and they don't retain that. But natural magnets do. They retain that acceleration. That's how they magnetize magnets. If you don't find them, a rare magnet in the earth already magnetized, you can make them, but they shoot an electric current through it. And what ferrite and other natural rare earth magnets do is when you shoot that electric current through it, they retain that. They don't not only obtain one-way direction of accelerated gravity, but they retain it. They retain it. And they figured out that neodymium, the particular components of it, you can look it up. I forget what all's in these or in rare earths, exactly what all the components are, but they are not electrically conductive, but yet it takes electricity to make this material magnetic. My point is ferrite is so important in the universe because it naturally stays that way. It stays, aligns gravity in one direction, in the south, up to the north, and then the north is diverted back around to the south. That's what gives your magnetic field. And that's what they do is automatically accelerate gravity because it's going in one way and it's got twice the distance to go. To feel this, the atomic strong force of all these atoms, it's going through it one way instead of all spherically radial to the core. You have to see my magnetism video to understand that. But my point is we get electric currents from magnets passing by copper coils. That's just how it works. I mean, you can use an electromagnetic field, which gives you that acceleration, but you can use magnets, and I've showed that in many videos, how I use my little AC generator or just running magnets through a copper coil, by neodymiums through a copper coil. You can get electric current. That's how it was first made, and now we've figured out better ways to do it with electromagnetic fields. But my point is, the ferrite doesn't retain continuity to conduct. It does not want to conduct an electric current, but it takes an electric current to make it a magnet. Isn't that a paradox? And even so, with the conductor that makes a magnet magnetic, it will conduct the electric current, but it doesn't retain the one-way direction that electric current went through it. So that was my whole point, is the difference between conductors and ferrite is that ferrite will retain it, and there's steel will somewhat retain it, but it still remains a conductor even though it retains magnetism. And copper or aluminum or just regular conductors that are not magnetic, because the copper does not stick to that, but the steel does. And just like this is magnetized. This little Phillips head from a screw drill. It's magnetized and it's steel, but it doesn't conduct as well as the copper. And it won't have near the magnetic power that a rare earth magnet will. So my point is that ferrite is not conductive. It will not conduct an electric current worth a darn. Steel does, and you can magnetize steel, but it doesn't magnetize as well as ferrite. And that's the whole point, is ferrite is so important in the universe because it has the opposing properties as opposed to conductors. It will accept an electric current and it will retain that. But a conductor will pass it on, accept it and pass it on, but it will not retain it. That's why it takes a magnetic field to make electric current. So I'm just pointing out that natural magnets are not conductive. I mean, you've probably tried this or know this. But there's a reason, and more than just there's a reason, the way that, if you saw my video on how magnets work, that ferrite and other materials they make natural magnets out of is special in that sense. It's the only one that will accelerate gravity through itself, but only enough to fill its own needs for its atomic strong force. And if you're trying to hit it with an electric current, it'll take it, but it'll not only take it, obtain it, but it will retain it. Conductors don't do that. They will take it and conduct it, but they do not retain it. And that's the conflict or the paradox of natural earth magnets. So the point is, it's a paradox. You have to have a magnet passing by or swinging around a copper coil to create electric current to make a magnet, which turns around to the beginning. That's what I'm saying. Everything in the universe is connected by the static charge. It's just the acceleration of the static charge, and what element is getting acceleration of how much is the display you get. But a magnet swinging by or passing by a copper coil makes an electric current, accelerates the gravity of that this is creating through something that does not want to be magnetized or having accelerated gravity go through it, but it conducts it, and then you can make another magnet, which will retain it. Okay, on the AC system, I'm going to show you on my little dryer or washing machine motor, brushless, which I told you the magnets are like north-south, 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 north-south as they pass by the coils. I want to make sure you understand and see that that's what's going on here. My compass will work with me. Sometimes it gets freaked out because they're so close together. Like you'll have a south, and it'll flip around to a north, and it'll flip around to a south, and north, and it'll flip around to another south. So if you see with the compass, it goes north, south, north, south, north, south. So we know we're doing AC current. We're pushing with the north, we're pulling with the south, pushing with the north, pulling with the south. So each one of these is going push, pull, push, pull. I want to make sure you understand that before I move on to metering what we're going to show on ions. And we'll move on. What I want to do here is remind everybody that when your AC current comes into your house and your appliances or your electronic devices have a transformer that's AC, and then it reduces that down to a lower AC. Somewhere in the device, there are several, if not one or more, bridge rectifiers, which means all the push-pulls go out one push and come back a pull. But most of the components of an electronic device use only the pushes, the north pushes of the AC, the one that's going out, going out, going out. The bridge rectifier, if you ever noticed, when you take an electronic device apart, the bridge rectifier, the north side is to feed the component inside. So the acceleration going into your components in your electronic devices, TVs, computers, anything, is going to be the north. When it turns it to DC, when it converts to DC, it uses the north push side to operate the component. That's whatever in your device coming from the AC current through the transformer, which reduces the AC back and forth down to a lower voltage. Then that goes to a bridge rectifier, and most of the components in your electronic devices will be hooked to the north side out, always the push. They don't need the pull. The south side, the south pull back on your AC system is not what it uses. It uses the north. So I want to make that very clear. And we'll move on. Okay, here's my microwave transformer. Got my W, and here's the cap that goes on top, normally when it comes out of the item, the microwave. And these rubber bands are just to hold it there when I store it or when I use it with the cap on. But I don't use them in this demonstration. So I'm going to take the cap away and put it over here. So I've got an open ends. And what I'm going to show you is that on the AC, like I showed you in the earlier section here, or a different section, was that most of your components only use the push side of the AC. It's pushing and pulling, pushing and pulling, pushing and pulling. But when it gets to a bridge rectifier, most of your components in your devices only use the push. The push is what runs things, then it comes around, and the pulls take it back. You rarely ever use the pull because the bridge rectifier makes only the pushes actually go out and do something. The pulls are the return. What I want to show is depending on, it's all accelerated gravity. And let me go back here to like I showed you in the earlier section, is that when you have an electric current and you push it through a piece of ferrite, you magnetize it. But where the current went in is the south, and where the current goes out is the north, and it'll be magnetized that way. And that's how you make magnets, right? It's acceleration, according to my theory, it's accelerated gravity is all electric currents are. And magnetic fields from an electric current is the same thing. It's accelerating gravity. But it depends on which way you're accelerating. And this is what I'm going to show with this little screwdriver tip from a screw drill, which is a Phillips tip into an extension. And right now it's magnetized. I'm going to demagnetize it. And I stand it vertical in the center post of my transformer, energize it for a second, and it's not magnetized. It pulls the magnetization out when you stand it up. And what I'm going to show is I can lay it sideways between the center post and this post where the AC current is going back and forth, back and forth, back and forth. And if I energize it for a certain amount of time, a quick flash, I'm north. It's magnetized now, and it's a north magnetization this way. That's north because it's the compass goes to the North Pole of the Earth, if you see. But when I put this near it, the north comes to this. So that made it north. And I have to do this just right because you have to catch the AC at the right flip. So I might be able to do it this way real quick. Same way again. And it's south. It caught the AC going back the other way because this connected these two together. It goes over, back, over, back, over, back. And without the cap, it's just shooting out, pulling back, shooting out, pulling back. And the center, same thing, shooting out, pulling back, shooting out, pulling back. And this side's the same thing, shooting out, pulling back. These two sides will be opposite. And the center will be opposite to those two. Like so. So I magnetized south now. As you've seen, the point was sitting the same way the last two times I did it. Let me demagnetize. It doesn't stick. No magnetization. And I can go on this side, quick flash, magnetize it, and it's north. Okay? We're north. The tip is north. It's magnetized north. And let me demagnetize it, which it doesn't stick. Really don't pull. And I'll leave it the same way again. I'm going to try to catch it right at the time the AC clashes now to get a south instead of a north. It's magnetized, and I'm south. I'm south. I caught the AC on the other cycle. That's all I did. Caught it on the other cycle. And that side will be north, this side south. What I'm saying is, the same thing is happening with electric current when you make a magnet, but with an electric current, on a DC especially, you know which way it's going through it. You know if you force the current on a DC this way through a magnet or through a piece of ferrite, it's going to be magnetized south input, north output. That's what I just did with this, and I showed you how a transformer will do that. If I stand it vertical in the center, it takes the magnetization out of it. And the point is, it's all accelerated gravity. This is accelerating gravity. Your secondary coil catches that. And depending on the number of windings of your primary coil and your secondary coil, depends on how much of that is caught, how much of that acceleration is caught. And if this is accelerating at whatever windings you have here, you have so much acceleration. And if you add or subtract the number of wires and the thickness of the wires and the number of turns, you will add or subtract the amount of acceleration going through. And that will be determined with voltage, ohms, watts, and all your measurements of what we say electric current is. But the point of this was to show you that it's all accelerations of gravity. It's all the same. An electric current through a magnet will magnetize it. A magnetic field through steel, which makes a magnetic field, also magnetizes. But that's an electric current. What I'm saying is they're both accelerated gravity. That's all it is.